We've seen some epic shots in basketball, but what if I told you that the perfect shot could come from some old men with some seriously unexpected style? Introducing the granny trick shot. And no, this isn't just a basketball shot, it's a full-on comedy sketch. Dude Perfect totally dresses up as old men to pull off this wild and hilarious shot. Have you ever watched a trick shot like this and wondered, how in the world did they make that incredible shot? Well, today we're going to break down this crazy half-court shot and model it with math. That's right, math. Specifically, we're going to use the vertex form of a parabola to model the exact path of this trick shot. Because if you think about it, every trick shot follows a curve, and that curve, you guessed it, it's a parabola. In this video, we're going to first determine how far the shot was and how high it reached. After that, we'll plot a path of the ball on a graph. We'll determine an equation to model height versus distance in vertex form, and use this equation to determine other characteristics of the ball's motion through the air. Ready for some math mixed with Dude Perfect? Let's see how we can track this shot's journey, whether you're throwing like an all-star or, well, like an old-timer. Now the first thing we have to determine is how far is the shot. He shot it from half court at the sideline, and then it went straight into the hoop. So that's a diagonal distance. Well, we don't have any diagonal dimensions here, so we have to look at the length of the court and the width of the court and put those together to form a right triangle. And so what I'm going to do is first notice that the distance it goes down the length of the court is not quite 14 meters because it's not going all the way to the end line because the basket's sticking out a little bit past the end line. And so we have to subtract 1.6 meters from that 14 meters. And we get 12.4 meters down the length of the court. And the width of the court portion is from the sideline straight across to the middle of the court. Well, that is half of 15 meters. So we divide that 15 by 2 and we get 7.5 meters. And because that forms a right triangle, that now allows us to use the Pythagorean theorem to solve for that distance that the shot was. And so what we're going to do is we're going to say c squared equals a squared plus b squared. Well, I'm going to let A be this 12.4 length up there. I'm going to let B be the 7.5 length, and C is what we're trying to solve. So we're going to write this as 12.4 squared plus 7.5 all squared, and that's C squared. And so C squared is equal to 12.4 all squared is 153.76. 7.5 squared is 56.25. So now what I do is I get c squared is equal to the sum of those two things, 210.01. But then to get c by itself, I have to take the square root. So the square root of 210.01. And I get a c value that's approximately equal to 14.5 meters. So we're going to use that as the length or the distance that the basketball was shot. Well, what about the height? How high did the shot reach? Well, in order to figure that out, we can look at the picture that we have here. You can see I stopped the picture of the video when the ball was at the highest point, and I'm going to compare the person standing there to the height of the shot, height of the ball. And so if that's 2 meters, then if I look at that, it's about 4 times the height of the person standing there. So I'm going to estimate that that reached a height of 8 meters for the shot. So how are we going to go and model that and find an equation? Well, what I've done to start here is I've noticed that it's going to be at a height of 8 meters, as I already mentioned. And we know that the shot had a total distance of 14.5 meters. And so what I'm doing is I'm saying, okay, it's going to go in at a height of just over 3 meters. That's how high a basketball net is. So I have the point here that I've labeled. This is going to be 14.5 and 3.05 meters. That's how high a basketball net is. And then I know that it's being shot from a height of about 1 meter high, so that's 0 and 1. And then I could see that I know that this is a height of 8, but then what I'm going to do is I'm going to recognize that I'm not going to be exactly in between 0 and 14.5, because 14.5 is higher than where it was released. So when I draw my curve through everything, I'm going to say, okay, that curve might go a little further out, maybe out to somewhere around 16. And so 16 when it's at a meter, roughly. And so what I'm going to do is I'm going to estimate that that's going to be about 8 meters in horizontal distance. So I have a vertex of 8, 8, and then I have 2 other points on the curve as well. And the ones I'm going to focus in on to form an equation with are these two because they're just the simplest ones to use. So let's look at building that equation now. So the vertex form of a parabola is y equals a times x minus h all squared plus k. And then what we need to do is we need to recognize that the vertex, as noted, is 8, 8. And so we're going to substitute that in for my h and k values. So this becomes y equals a times x minus 8 all squared plus 8. And so now what I want to do is I want to sub one other point in because I need to solve for a. So I'm going to substitute in the point 0, 1 is x and y. And I chose those 2 points because those 2 points were the 2 easiest points. I could have used this point as well and it would have given me similar value, but I chose to use those 2 because they were just the easiest ones to use. So if we substitute that point in, we get 1 equals a times x was 0, so 0 minus 8 all squared plus 8. So now I'm just going to rearrange this and solve for a. I get 1 equals a times negative 8 all squared plus 8. Now what I want to do here is I want to go ahead and I want to subtract 8 from both sides. So let's sub that in now. So y is 1, and so 1 equals a times 0, x becomes 0, minus 8 all squared plus 8. And so now what we want to do is rearrange that for a. So the first thing I'm going to do here is I'm going to subtract 8 from both sides. So that's going to give me negative 7 equals a times 0 minus 8 is negative 8, and then that's squared. So this gives me a times positive 64, or 64a. Dividing both sides by 64 gives me a value of a is negative 7 over 64. I'm going to keep it like that, though I could round it, because that's just going to give me a more accurate answer. So my equation becomes this. My equation is y equals a, well that was negative 7 over 64, times x minus h. Well, h was 8, all squared, and then plus k. K was also 8. And so that is our final equation that represents this situation, and it's exactly the equation that models what the dude perfect trick shot was. Now, I don't think this equation was running through their head when they did this, but we can model that out and see exactly how it works with math. And so now let's solve a couple of problems with that. The first problem is this. What is the ball's height when it's traveled a horizontal distance of 10 meters? All right, so what we're going to do here is we're going to sub in x equals 10, because x is the horizontal distance in this equation. So y equals negative 7 over 64 times 10 minus 8 all squared. We replace the x with 10 plus 8. And so we're going to use BEDMAS, the order of operations, to solve this. So 10 minus 8 is 2. 2 squared is 4, which we'll do in a moment. And so we're going to get negative 7 over 64 times 4 plus 8. And so that gives me negative 28 over 64 plus 8. And so really that's 8 minus 28 over 64. And when we do that, we get a value of 7.5625 meters, which is approximately equal to 7.6 meters. So the ball's height when it's traveled a horizontal distance of 10 meters is 7.6 meters. Let's go back to the graph now and see how that compares to what we had on the graph. So you can see at 10 meters, that's the point right there. And you can see that that's about midway between 7 and 8 meters on the vertical axis. So 7.6 isn't too bad. Maybe 7.5 would be a little better. But we're not going to have a perfect model for this. And so that's pretty close. And so that is a very legitimate answer based on the model that we've made. And the last question says this. At what horizontal distance was the ball at a height of 5 meters above the ground? Well, that means that y is actually 5. We're not doing x this time, we're doing y. And so if y is 5, we have to solve when 5 is equal to negative 7 over 64 times x minus 8 all squared plus 8. We need to solve for x in this case. And so what we have to do is we can rearrange this by bringing the other variables over. And so what I'm going to do first is I'm going to subtract 8 from both sides. And so this is going to give me negative 3 equals negative 7 over 64 times x minus 8 all squared. Now I'm going to multiply both sides by negative 64 over 7, because the 7 on the top is going to cancel out with the 7 on the bottom. The negatives will cancel out, and the 64 on the bottom will cancel out with the 64 on the top. Well, whatever you do to one side, you have to do to the other. So we need to multiply this by negative 64 over 7. And so what that's going to give us is it's going to give us 192 over 7. And that is equal to x minus 8 all squared. Well, how do you get rid of the square? You take the square root. Now the thing to keep in mind here is we actually don't just take the square root, we actually take the positive and negative of the square root. And if you want to know why, it comes down to something like this. If I told you that y was equal to 9, or rather y squared was equal to 9, then you would say, well, y could be equal to positive 3, or y could be equal to negative 3, because negative 3 squared is also 9. So what did you do? Well, you took both the positive and the negative square root of 9. And so you have to do that anytime you have an equation like this. And so now we get plus or minus the square root of 192 over 7 is equal to x minus 8. Now to get the 8 on the other side, we have to add 8 to both sides. We're now working inside those brackets of x minus 8. So that's the last thing we're doing here. And I could add 8 after the square root, or I could add 8 before the square root. The order of addition doesn't matter. So I'm going to write that as positive 8 plus or minus the square root of 192 over 7. And that x is now by itself. And so if you put that in a calculator, what you get is you get two different answers. You get 8 plus the square root of 192 over 7. That's one possible answer for x. Or x is equal to 8 minus the square root of 192 over 7. And so if I go 8 plus the square root of 192 over 7, I get an answer of approximately 13.237 meters. But if I go 8 minus that, what I get is an answer of 2.763 meters. Both of these are approximate. They're rounded to 3 decimal places. So let's go back to our graph and compare and see if this makes sense based on the graph that we made as well. So remember, the question was asking us at what horizontal distance was the ball 5 meters above the ground. And so if we draw a line, a dotted line across at 5 meters, we get two different x values. We get one here, which corresponds quite nicely to 2.763 meters. And we get another one right here, which corresponds quite nicely to 13.237 meters. And so again, that suggests our model is actually quite accurate, and we've now been able to solve a couple of problems using Dude Perfect's trick shot. If you found this video helpful or informative, please click like and subscribe. It would be really helpful so I can keep making videos like this. For another example of going from a graph to an equation, click the video on the left. If you want to see one simple method to factor any quadratic, check out the video on the right. Thanks so much for watching.